Scientists just discovered dark matter might have existed before the Big Bang itself. This discovery shatters everything we thought we knew about the universe's beginning. You're about to journey through quantum realms where nothing teems with invisible energy, witness cosmic collisions that birth entire realities, and explore laboratories where physicists create universes from pure mathematics. Stay with us. The unknown awaits. Like and subscribe for this mind-bending expedition into the impossible. Empty space refuses to stay empty. Scientists have discovered that what we call vacuum actually seethes with constant activity at the quantum level. Picture the surface of a perfectly calm lake. From a distance, it appears motionless. Zoom in and you'll see molecules dancing. The quantum vacuum works similarly. These quantum fluctuations represent the temporary appearance and disappearance of particle pairs. Heisenberg's uncertainty principle demands that energy cannot be precisely zero even in empty space. This means the quantum vacuum must contain some minimum energy level, the ground state. This ground state can fluctuate, allowing virtual particles to pop into existence before vanishing again. These processes are measurable. The Casimir effect and Lamb shift are experimental evidence. These are not mere theories. They are measurable consequences of quantum vacuum energy. Einstein's E equals mc squared means vacuum energy can transform into real particles. European researchers use the world's largest X-ray lasers to directly probe vacuum fluctuations. If successful, these tests could confirm fundamental predictions of quantum electrodynamics. If the vacuum is a seething store of potential, then instead of nothing, we begin with a field of possibility. When fluctuations separate pairs, one can become trapped inside a growing bubble and evolve into a universe. Modern physics forbids absolute nothingness. Quantum mechanics requires fluctuations. So we must ask, how did our universe emerge from this ever-present quantum vacuum? Some physicists propose our universe began as a quantum fluctuation that became self-sustaining. Next, the discovery that challenges the beginning itself: dark matter before the Big Bang. Dark matter outweighs visible matter by roughly 5-to-1 and shapes cosmic structure. Yet scientists have never directly detected it. Its origins remained unknown. Groundbreaking research published in 2024 suggests dark matter might have formed before the Big Bang. University of Texas researchers developed a model called WiFeY, warm inflation freezing. Their calculations show rare interactions during inflation could produce dark matter particles. The extreme heat and energies of inflation triggered processes that can create and preserve these particles. Computer simulations using WiFeY reproduce patterns in the cosmic microwave background. The cosmic microwave background carries the imprint of the universe's earliest moments. WiFeY's outputs match observed relic radiation patterns, suggestive but theoretical. Catherine F. Eves explains these interactions were rare but predictable consequences of known physics under extreme conditions. Think of inflation as a massive factory where rare kernels survive the chaos and become dark matter. If dark matter predates the Big Bang, our cosmic timeline becomes more complex. What other components might have existed in this pre-cosmic era? The model remains theoretical and needs future observational tests. But if correct, the finding forces a rethink of the universe's origin story. Next, the inflationary epoch that set the stage for everything that followed. In 1980, Alan Guth proposed cosmic inflation, a breathtaking exponential expansion before the Big Bang. Picture a deflated, wrinkled balloon rapidly inflating into a smooth sphere. Inflation solved the horizon and flatness problems by stretching space and smoothing irregularities. The energy driving inflation came from the inflaton field, a form of matter with repulsive gravity. Under extreme conditions, general relativity allows for repulsive gravity that drives expansion. In 2014, gravitational waves in the cosmic microwave background provided direct evidence for inflation. But inflation may not stop everywhere. Eternal inflation suggests inflation continues in some regions forever. We live in a pocket universe, one bubble among an eternally inflating foam. Paul Steinhardt and Alexander Vilenkin formalized how quantum effects can sustain eternal inflation. Chaotic inflation predicts a self-reproducing multiverse where all possibilities appear somewhere. An infinite multiverse makes probabilities murky. Every outcome happens infinitely many times. This creates deep mathematical and philosophical paradoxes. Virtual particles live secret lives in empty space, popping in and out of existence. At the Planck scale, values of energy, time, and space fluctuate randomly. Causality loses meaning. Energy can be borrowed from the vacuum briefly, a cosmic bookkeeping loophole. Random quantum fluctuations can, in rare cases, seed regions that grow into entire universes. Across the multiverse, all physical laws and constants may be realized somewhere. But Stephen Hawking spent his last years trying to tame the infinite multiverse, to make cosmology testable. Stephen Hawking spent his final years taming the infinite multiverse. Hawking argued that an infinite, untestable multiverse fails scientific predictability. Working with Thomas Herto, Hawking applied holography to project out time and simplify eternal inflation. Their approach studies the universe by examining a spatial surface at the past boundary, removing time. They predict a globally finite, smoother, large-scale universe, reducing the range of possible universes. Herto plans to test the model by searching for primordial gravitational waves, a smoking gun. Alternative models propose the Big Bang was a bounce, one in an eternal cycle of expansions and contractions. In cyclic cosmologies, the universe rebounds instead of collapsing to a true singularity. Some research suggests primordial black holes formed during contraction could be viable dark matter. Each model faces observational challenges. Rigorous tests are essential. Cosmology's central challenge is testability. Can we observationally distinguish these models? Primordial gravitational waves remain one of the best observational discriminants. Hawking's holographic approach makes inflation more predictive and thus more testable. Whether finite or cyclic, these ideas push the boundary between physics and philosophy. String theory replaces point particles with tiny vibrating strings across extra dimensions. How these extra dimensions fold determines the laws of physics in a given pocket universe. In some models, enormous membranes collide in higher dimensions, and those collisions can birth new Big Bangs. Imagine our universe as a soap film. When films crash, they create ripples, a new universe. This episodic cyclical picture avoids singular infinities and can repeat forever. String theory even predicts cosmic strings, structures we might detect in the CMB. From vacuum fluctuations to pre-Big Bang dark matter, from eternal inflation to Hawking's holographic solution, our picture of beginnings keeps evolving. The greatest mystery may not be what caused the Big Bang, but what was already there waiting. Where are you watching from and what time is it? Let us know in the comments below. Like and subscribe for more. Stay sharp. The journey only gets stranger.